Hello guys, this is Sumadhur. Today we'll be covering linear programming, um, module B in the book textbook of Principle of Operational Management, 12th edition, by Heizer and Munson. So the first things we need to know is that linear programming is widely used application or a methodology that is used by operations manager to plan and make the allocation of scarce resources, either to maximize the profit or minimize the cost. Now, this duality of either maximizing the profit or minimizing the cost, it stems from the microeconomics, wherein you may have come across the duality of the problem, which is like two sides of the same coin. So in the business, either you can try to maximize the profit or try to minimize the least cost under the any given circumstances. So for the linear program, there are a few things that we need to take into account. For the first thing is the art side of it, which is formulating the problem. Once you have the problem formulated, then the science part of it starts, wherein you want to make sure that the mathematical problem represents to the best possible ability and takes into account the things that are relevant for the business. So to begin with, we're going to start with the example that is given to us in the textbook, which is from the Glickmans. So let's see, the Glickmans have the option to make the xpods and the blueberry, and so they are making a certain combination of xpods and blueberry. One of the extreme cases could be that they can either make the xpods only and or the blueberries. So if they were to make only the xpods, then they can make certain amount of profit. If they were to make only blueberries, then they'll make certain amount of profit. And if they were to make a certain combination of either both of these products, then they'll make certain profit. But the idea is to maximize that profit such that they take into account the limitations that exist. So let's see how we can formulate the problem first. Okay. So the first thing we need to set up is we need to set up an objective function that determines as to what we are trying to do, or how we are trying to approach the problem. So since it is a profit, the more the profit, the better it is. So we want to maximize our profit such that we say we make xpod as x1s, and we make certain number of blueberries. Now we know that our xpod, we are shown here, it sells for $7 and blueberries sells for $5. So we are going to make 7x1 and 5x2. That represents our profit function. Now the profit is more the better, so we are going to say that this is, we want to maximize this. So if you were to make 1 unit of xpod, and this is blueberry. Now if you were to make 1 unit of xpod, then we'll make 7 times 1 plus 5 times the number of blueberries, let's say that be 2. Then the profit we make is $7 plus $10, which is equals to $17. Yeah, so this is our profit function. Now if this is the case, then we can hypothetically say that why don't we make as many xpods as possible and as many blueberries as possible. Yeah, that is what we should be aiming for. However, there's a limit, because for every xpod we take certain amount of time from the electronics department. Okay, so if that's the case, then we spend 4 hours in making that 1 unit of xpod. So on the similar lines, we spend 3 hours in the electronics department on 1 unit of blueberries, and the total amount of time that we have spent so far would be 4 times 1, because this is the profit that we calculated in this scenario is 1. So far we have spent 4 times 1 and 3 times 2. Okay, so that is 4 plus 6, we've spent 10 hours worth of time in the electronics department. At the same time, when we are trying to do the assembly, we spent 2 hours per unit of xpod, so it stays 2 times 1 plus 1 times, which is here, 1 times 1 times 2, because we use the 2 as the example, so it's 2 plus 2, so we've spent 4 hours. Now, so far this is going on an example if we were to make 1 unit of xpod and 2 units of blueberries. Okay, so this is what we call as calculated values so far, and it's also referred to as left hand side variable, and we'll see how. Now, the condition that we are given is that so far the total amount of time available for us is for the electronics is 240 hours per week, and for the assembly it's 100 hours per week. So these calculated values should stay less than or equals to, so let's see if I can slide a little bit more. So at this point, all of these values should stay less than 240 hours, and this has to stay less than 100 hours. So if we were to change any of the numbers, if we were to change these values, let's say instead of 1 we were to say now this is 100, and let's say we want to make 200 of this, then accordingly our new values would multiply it again by 4 times 100 plus 3 times 200. Okay, so we keep changing these variables, and that is why they are referred as x1 and x2 as to whatever they may be. But let's say if they were to be 100 and 200, then this becomes this equation becomes, oops, come on, okay, so this becomes 400 plus 3 times 2, that is 600, which means that we've already spent 1000 hours. Now remember, we only have 240 hours available, so this will no longer be less than 240. Therefore, we want to figure out what number is the best for both xpod and blueberries, such that our profit stays maximum without violating either of the constraint. Okay, so let's see how we can get this done in a spreadsheet format. So to keep things organized, the pattern that I use is to list the decision variables first. Decision variables in my case, in this case, is let's say x1, x2, wherein x1 represents the xpods and x2 represents the blueberries. Okay, now zoom that in a little bit, and because I want to use them in a calculations such that they are useful to me, I'm going to label them as a color that is easily noticeable for me. And then I know the price as well. For xpod, it's shown to us as $7, so I'm going to write that down, 7, and then Control Shift 4, oops, not yet, Control Shift 4, that converts it into dollars. And this one is for $5, Control Shift 4, that converts to dollar format. So I will calculate my profit here, oops, profit here, which is equals to some product of the cells to the left, and I'm going to freeze it by hitting F4, comma, select the cells in yellow. Oops, the other way around. I'm going to select the cells to the left, and I'm going to keep them free, comma, the cells that are my decision variables, and freeze them as F4, close the parenthesis. So if I was to go back to the example that we were just following, at this point, if I can punch in the values, let's say 1 and 2, that calculates the profit for me. If I was to say 100 and 200, then it should correctly give me the profit. And let's hit Control Shift and 4 on this cell as well. So then now it's in dollar format. Now let me keep these as 1 and 2. Now this is only to keep checking your calculations, that all your calculations are working correctly. And let me label this as green and the format. Okay, now the reason we should not be, we looked from this example when we are formulating this, we cannot make 100 and 200 because this calculated value 1000 has to stay less than 240. So let's first lay out the constraint. Let's say constraint A for electronics. If we make 1 xpod, then by that time we have already spent 4 hours on this, and this information is given to us. Yeah, so 4 hours and 3 hours for the blueberry, and the amount of time for the next limitation that we have is in assembly, wherein we spent 2 hours on 1 xpod and 1 hour in assembling 1 blueberry. So if you times 3, 6 hours in the electronics, and we've spent 1 times 2 in terms of assembly. So far we've spent 4 times 1 plus 3 times 2. So it is 4 plus 6 equals to 10 hours. And by this time we've spent 2 times 1 plus 1 times 2. So we've spent 2 plus 2 hours in assembly time, which is 4. Okay, so since we want to keep changing these numbers x1 and x2 such that this number is maximized, the profit, and these two numbers stay less than or equals to the 240 and 100 hours respectively that are given to us. Okay, so let's see how to do that in spreadsheet. First thing, if you froze your decision variables, which are currently in the yellow, if you froze those cells, then the benefit of doing that is that you can bring them down and copy them as formulas. So if you were to select any one of them and hit F2, it saves us a little bit of time moving forward, because we will be repeating this number of times again and again for this chapter. So the decision variables times the coefficients for the constraint. So what it does is 4 times 1 plus 3 times 2, and that is 10 hours. So this is what we call calculated left hand side variable. Now the given right hand side variables is 240. So our calculated values, which are, let's say in blue, has to stay less than or equals to the given variables, which is, let's say, represented in grayish color. So for assembly, it's 100 department. Now what we want to try is that keep changing these x1 and x2 such that our profit keeps on increasing. Let's say 10, 20, our profit goes up, and we have to make sure that these two numbers stay less than the given numbers. Okay, there are a few things that help us do this. One of them is using the data solver, that is a built-in add-in in the Excel. So it's called Excel solver. So if you don't see that in your on your spreadsheet, all you have to do is go to File, Options. Within Options, you have to click on Add-ins. Once you get the add-in, you have to make sure that you choose Solver add-in, and then you hit Go. Okay, once you hit Go, then you'll see the list. Now make sure that in your case, this Solver add-in is checked, and you hit OK. Okay. Now then I go to the Data tab and I click on Solver. Now within Solver, we will ask the spreadsheet that this is my profit function. This is the objective function cell that I want it to keep track of, and this has to be checked on maximize. Had this been a cost, then we would have checked this minimization, because then we would want it to minimize. But at this point, it is correctly by default on maximizing. By changing the variable cells in yellow, these are my decision variables, such that, come on, here, okay, why? Okay, profit function is this. By changing the cells in here, such that this blue cell has to stay less than or equal to, which is already there, 240. Add this calculated value for assembly has to stay less than or equals to the constraint for it, which is 100. So since this is my last constraint, I would hit OK instead of adding. At this point, we want to make sure that this variable is checked to make sure that these x1 and x2 cannot be negative. So either I make xpod or I do not, which means it'll be either positive number or 0. But there's no such thing as making a negative number of xpods or blueberry at this point. And choose the algorithm, that is simplex LP, and then hit solve. If everything is modeled correctly, then this is the dialog box that you'll get to see. Now, if there's something goes wrong, it'll come up with an exclamation mark, which just means that you have to fix the problems. Now, this is the ideal case scenario, wherein we found that the Excel told us that after changing all of these numbers a couple of times or multiple times, because the computer is faster than us, we should be making 30 of xpods and 40 of blueberries, such that our profit stands at $410, and we end up using all of our electronics time of 240 hours and all of the assembly time, which is 100 hours. Okay, now there are a few things that we need to pay attention. Again, if I was to go back to the solver window again, and I'm just hitting solve. So if you notice at this point, it says keep solver solution. That is what allows us to see the number that that maximized our profit. So if we were to choose, if we were to say 30 and 40, if we were to choose restore original values, then we will lose these numbers. Now, if you also see at this point, there is something called sensitivity. We will look at this again in a different problem, but at this point I want to stop here in terms of solver, but give you an idea as to how we would have solved this on paper. Okay, now let me bring the notes here. So if this was to be our case, so far what we are saying is here. Okay, what we've done so far is that we've found the decision variables x1 and x2. The value for this x1 is 30 and 40. Now this is coming from the spreadsheet. In the old days, when not everybody had access to the spreadsheet, this could have been solved by arithmetic or algebraic way. One of those ways is called as graphical solution, which is only helpful when the problem or the constraint is simpler. No more than 2 constraints ideally, or let's formulate that. So we had the problem 7x1 plus 5x2. This was our profit function and we wanted to maximize it. Our constraints were 4x1 plus 3x2, and this had to be less than equals to 240. We also had the second constraint for assembly, which is 2x1 plus 1x2 less than equals to 100. Now this is our constraint A, this is our constraint B. Okay, now the moment we change x1, all of these variables have to be calculated such that you would have a value for 4x1 plus 3x2, x2, for any value other than 30 and 0. Okay, so every time this has to be recalculated. So this, if you were to do that in Spreadsheet, it allows us not to have to recalculate multiple million number of times to find out a profit that is maximum and all of these conditions are met. So if I was to name this as equation 1 and this as equation 2, and we want to see as to graphically what does it mean. So let me see if I can. If I was to deal with equation 1 at this point, then what I can say is at x equals to, at x1 equals to 0, this equation becomes 4 times 0 plus 3 times x2 equals to 240. Now this is just trying to solve for x2. Therefore this becomes 0. We are left with 3x2 equals to 240. Therefore x2 is 240 divided by 3 equals to 80. So at x1 equals to 0, x2 is 80. Now at x2 equals to 0, let's solve the equation 1 again. Okay, now this is all using equation 1. Okay, so at x2 equals to 0, let's see what it becomes. 4 times 0, 4x1 plus 3 times 0 equals to 240. Therefore it's 4x1 plus 0 equals to 240. Therefore x1 equals to 240 divided by 4. Okay, therefore x1 equals to 60. Okay, so let's bring these two information together. This at x1 equals to 0, x2 was 80, x1 is equals to 60 when x2 is equals to 0. If we were to plot these 2 points, we will come up with a line segment such that if this is x1, if this is x2, such that 10, or let's say 10, 20, 30, 40, 50, 60, 70, 80. Okay, and similarly 10, 20, 30, 40, 50, 60, 70, 80, 100. Okay, now when x1, if we were to plot this at x1 equals to 0, so x1 equals to 0, x2 is 80, so 20, 40, 60, 80. So this point is what represents as 0, 80. Okay, the next point is at x1 equals to 60, so 20, 40, and 60. Okay, so at this point x1 is equals to 60 and x2 is 0. So if I was to represent this again in x comma y format, then this would be 60 comma 0. So now I have 2 points. If I was to join, then any of the area, because our equation 1 was again 4x1 plus 3x2 less than equals to 240. So since it is a less than or equals to, that means anything less than or towards the origin, okay, all of this triangle, any combination of x1 and x2 will give us a profit. But in order to maximize, we maybe have to somewhere on this line, this is also called as isoprofit line, okay, because at any given point in this time, your profit would be the same. But this is only one constraint for the electronics. The second constraint we have is for the assembly. So let's solve for the assembly constraint as well using equation 2. Let's see what our equation was. If you notice, for the equation 2 we had 2x1 plus 1x2 less than equals to 100. So we are going to do the same calculations that we did for equation 1 to find out 2x1 plus 1x2 less than equals to 100. Okay, this time I'm going to cut down some of the steps. At x1 equals to 0, x2 is equals to, so x1 is 0, so this term becomes 0. 1x2 equals to 100, so x2 becomes 50. Okay, or the other way around, we want to find out what x1 is when x2 is equals to 0. So when we put x2 equals to 0, this whole term becomes 0. So it will be 2x1 equals to 100. So x1, what did I say? Yeah, x2 is equals to 0. Therefore, x1 will be 50. Okay. Oh, something looks funny. So let me check this. X1 equals to 0. This becomes 0. X2 is equals to 100. Okay. And when x2 is 0, this is 0. X1 is equals to 50. Yeah. So let's try to plot this one on the same graph. When x1 is 0 and x2 is 100, when x1 is 0 and x2 is, so this is 60, 70, 80, 90, 100. Okay, so this is 0, 100 point, and the next one is 50, 0. So 30, 40, 50. So this point is 50, 0. So if I was to join this, okay, almost there. So anything towards the origin is the area that is feasible based off of this constraint. Okay, now if you notice, there is an area, let's see which is visible, between this line and this line. Okay, this area which is towards the origin for the first equation is excluded when you also take into account the second constraint. Okay, so if we were to take into account only the constraint for electronics, we could have been here, so certain amount of x1 and certain amount of x2, but this point is not feasible because of the constraint for the assembly exclude this area. So now the common area between these two is only from here onwards towards, or let me use this one, this and this. So the electronics constraint does not allow us to use this much, and the assembly constraint does not allow us to use this area. So the common area that meets both of the constraint is in the yellow side. Okay. So as you can see, this is only helpful when you only have fewer constraints. Otherwise, you'll end up doing all these calculations for every equation. Now, at this point, we see that there's an intersection. Okay, we know that when we looked at, let's say we have a choice of not making any xpods or any blueberries, which would be 0x1 and 0x2. At this point, our profit would also be 0. If we were to be at 0, 80, which means we make 0 of xpods and 80 blueberries, then we'll have a certain profit. We can also make 50 xpods and 0 blueberries. Okay, at this point also we will have a certain profit. At this point we would be making 30 of xpod and 40 of blueberries. How do I know this? I know this from having solved this. But if we would have not reached this stage, then the way you would solve this using the graphical method, or what they also call as corner point solution, is you would solve for equation 1 and equation 2 together, which means our equation 1 was 4x1 plus 3x2 equals to 240, or let me say at this point less than 240, and 2x1 plus 1x2 less than equals to 100. So at this point my intention is to remove one of the variables such that I can find the value of the other. So oops, a little too much. So I'm going to perform equation 1 minus 2 times equation 2, because I'm multiplying the full equation by a number, so my equation stays unchanged, which means I will be dealing with 4x1 plus 3x2 minus 2 times 2x1 plus x2 less than equals to 240 minus 2 times 100. Okay, let's solve for it. So this equation 1 left hand side is same. Yeah, this part has to be multiplied by 2 and then subtracted. Okay, so it becomes 4x1 plus 3x2 minus this 2 times 2, 4x1, and 2 times x2, and you remember this, there's a negative sign in front of the whole thing, so this becomes negative and this also becomes negative, minus 2x2 less than or equals to 240 minus 200. Okay, so we see that 4x1 and 4x1 get cancelled out. We are left with 3x2 minus 2x2 coming from here. So we are left with x2 equals to 240 minus 200. x2 is equals to 40. Now using this, you can put this value in either of the equation to find out the value of x1. So let's say I want to use the second equation because it seems to be easy, because I know the value of x2. Okay, would require least amount of calculation. So if I was to use equation 2, then we can say 2x1 plus 40 less than 100. Therefore 2x1 less than equals to 100 minus 40. Therefore x1 has to be less than 100 minus 40 is 60, and this 2 goes to denominator by 2, which is 30. Yeah. Come on. X1 has to be or equals to 30. So we know at x1 equals to 30 and x2 equals to 40, this at this point it is part of both the constraint equations, which were x1 come on. So at x1 30 and x2 40, both of these lines intersect, both of these constraints intersect at that point. So if you come back at our graphical solution, solving for these two equations, equation 1 and equation 2, 2x1 plus x2 less than equals to 100, this point satisfies both the constraint. So now we know at this point, this point, this point, and this point, these 4 points are easily found by solving the equations algebraically. If we were at this point, that is not a good point for the business, because theoretically it says we are making 0 xpods and 0 blueberries. At this point we are saying we are making 50 xpods but 0 blueberries. At this point we are saying we are making 0 xpods but 80 blueberries. Okay. At this point we are saying we are making 30 xpods and 40 blueberries. However, this is the point that is the farthest from the origin. So that means that this is the point where our profit is maximized. If you were to take the direct distance between this point and this point, that is what represents, that is the farthest distance from the origin, and therefore this is called as the maximum profit. Therefore you'll also come across in textbook that says corner points solution method. So this is what that means. Okay. Now you'll realize that all of this is good to do, but it becomes soon complicated. I mean, it's complicated even for the doing it for the first time, just for the understanding. But if I have to plot this using the graphical method, it's not always, let's say in today's world, I mean, it's not always the best way to go about it. Yeah. So if I have to draw this more neatly, I mean, let's see how we can use Spreadsheet to do the job for us. So let me bring this, the basic required information. So using equation 1, or let's say for the constraints of electronics, let me copy this, paste it here. So I'm going to still use the same format or same pattern, so then I can keep track of things, because we will develop this pattern and follow it again and again for the rest of the problems in the chapter. So at x1 equals to 0, let's see, what did we solve from this one? Oops. Oh, come on, I don't want to see this. Okay, there. So at x1 equals to 0, at x2 was 80, and then when x2 was 0, x1 was 60. Okay, now this was for equation 1. Then using second equation, which is for the constraint of assembly. Okay, when x1 is 0, x2 was what equation are we using? This is equation 1. Okay, where's the equation 2? At x1 equals to 0, x2 is 100. When x2 was 0, x1 is 50. Okay, now let me move it one more down, and let me bring this one here. Now the only reason I'm doing this is because I know sometimes, how the spreadsheet names it. Okay, so it will help me now in the labeling. So let me select the cells here and insert what we call as scatter plot. Okay, now sometimes the spreadsheet will try to be smart, so we'll have to be careful. As of now, I'm going to do anything that it allows me, and then later on I'll try to fix it. So let me maximize this. We have all of these values in here. Okay, so let me bring this here. Okay, now if this is the format, it is relatively easier for me to say, where's add labels? So far it doesn't allow me to add labels. Let's say click on empty area, then left click on one, right click, and then add data labels. And let me use the callouts. Okay, so as of now it is representing this as 060 and 80. Okay, but that's not what we want. However, let's select the data series. This is the name of the series. All the x's would be 0 and 60, and the y's would be 80 and 0. Okay, hit OK and OK. Okay, so where did my callouts go? I'll add them later. The next thing is select more data, add one more series such that the name is constraint assembly, and I'm going to select all my x's and all my y's. Remember, these are all in the same format: x comma y, x comma y. So I'm selecting y's at one point in time, and we already selected x's. Okay, then hit OK. Now if everything has been labeled properly, then now we can say, oops, let's select it, empty area, left select one of these points, add data labels and callouts. Same thing for this series, add data labels. I'm going to add callouts. Now the spreadsheet is still denoting only these points, but because of the type of graph that we chose, remember when we had the format or the design, let me show it like this. If we were to select chart type, we were to select only the points, then this is what the actual graph is. But we are trying to use the spreadsheet to join these data points such that it looks to us that they are the lines, but they are not actually the lines. Okay, so we are going to choose the connected dots such that it serves our purpose. So the way we would understand this is, given these constraints, okay, given these constraints, this is the area to the left of which is met by the constraint for electronics. Yeah, let me show the labelings. What I meant to say was legend. Okay, so the blue one is the constraint for electronics. See, the labeling helps us understand. So anything towards the origin, that's what this one helps, and anything towards the origin for the assembly, okay, which would be starting from this point towards this. So this is one corner point, this is the corner point, second, the third, and the origin itself. So 0 comma 0, 0 comma 80, and 30 comma 40, and 50 comma 0. These are our four corner points. Now the reason I'm highlighting is because these are some of the things that may be asked or things of our interest moving forward. It's not something that we have to do it for every problem. Same thing goes for the algebraic solution that we did. Now, if we were to look at only one constraint at a time, the constraint of electronic includes this area, yeah, this area, but this area is not included by the assembly constraint, yeah, because we have to also stay less than the constraint assembly, the constraint for the assembly. So this area is included by the electronics but not by the assembly. Similarly, this area is included by the assembly but not by the electronics. So this is the point wherein the constraint for electronics and assembly are equal, and therefore this is the point where we can maximize our profit, because that is the farthest away possible point from the origin wherein both of these constraints are satisfied. Okay, so this is how we do the graphical solution in Excel without having to use the freehand pen and paper like I did. I had to do it in terms of solving or explaining here, right? It looks a lot more messy. This is a lot useful if we are forced to do it, either for the purpose of explaining it or showing it to the audience or for some reason. Yeah, it also helps put a picture in mind if there were to be some of the constraint wherein it says it has to be at least a certain number. Okay, if that was to be the case, if these equations were to be instead of less than equals to, if this equation was greater than or equals to, now this is, let's say, for the electronics, then electronics is the blue. That means any area towards this side is the feasible solution. When I say feasible, that's where our profit has to be. Okay, if the assembly was to say that it has to be greater and not equal, which means the assembly is the orange line. So it means that anything towards this end, okay, let me choose different color. So anything towards the northeast side of this line, not including the points on this line itself, because it says greater, but not greater equals or greater than or equals to. So it cannot be equals to. So anything greater than the constraint of assembly is the feasible region. Therefore, the common region between the two would be starting from here onwards towards this direction. Okay, so but this is how it helps us picturize things. Now this is not something that is given to us. I'm just showing it to you just for the sake of example. Okay, now while we are at this example, let me also show you, remember I moved out of the linear programming of the solver itself. If, let's say, after having solved all of this, we come to this dialog box, then we left click on this called sensitivity and then hit OK. At the bottom you will notice a new report being generated. Okay, let's see the sensitivity report. Now let's understand this sensitivity report such that I'm going to bring in view, new window. Okay, and here, so I have the example. This is what we had here, our problem. Such that, let's see what all things we can look at from the sensitivity report. Sensitivity report tells us a lot of information in very compact form for most of the what if scenarios that are possible for the linear programming. And the first thing is that it shows what are the final values of resources that were used. So we ended up using 100 out of 100 available and 240 out of the 240 available. So, and if you notice, the way these cells are named is F9, F9. However, that F9 does not tell me the whole story, but the way it names them is it finds the first alphabet, constraint B assembly, and the first alphabet going towards the top. So constraint electronics calculated at LHS, that is the name it gave for this blue cell here, the calculated value, which is 240, and the first left cell and the top alphabet cell is how it named this 100. So first thing, that this cell is named constraint B assembly and constraint LHS, left hand side, and the amount that we ended up using. Okay. The next thing interesting is the shadow price. Let's talk about the shadow price for the electronics. Okay. So the shadow price for this constraint is 1.5. Now, what 1.5 means is that this is the amount if we were to relax our constraint by 1 unit, which means if we were to go from 240 to 241, so if you were to relax this constraint by 1 unit, so if you were to get one more R for the electronics department, then our objective function improves by the shadow price amount. Okay, so if we were to relax our constraint for the electronics by 1 unit, then our profit would improve. Improving in profit would mean that our profit increases by $1.5. So instead of 410, we will have $411.5 if we were to add one more hour to the electronics. So if somebody in the electronic was to work for 1 more hour per week, then our profit goes up by $1.50 more than the $410. Now, somebody might get greedy and say we'll make everybody work overtime 500 hours a week. Nope, that's not possible, because this shadow price is valid only within the range of increase of 60 and a decrease of 40. So if we wanted to increase 240 plus 60, or we can go 240 minus 40. This gives us a range of 300 and 200. So between the electronics department such that they have a total available hours of 200 and 300, we can still make 30 and 40 units. However, we will get $1.50 worth of change for every one more unit or one less unit. Okay, so if you were to go above 240, you will add $1.50 to your profit. If you were to go below 240, you would lose $1.50 for every 1 hour that you take away or add to the electronics department. Okay. Similarly, the shadow price of 50 cents for the assembly department means that we can this is the assembly department. Okay, so let's talk about the assembly department. The allowable increase is the allowable increase is okay, allowable increase is 20 and allowable decrease is also 20, which means anywhere between 100 minus 20 and 100 plus 20. This 100 is coming from the right hand side variable for the assembly department. So we have a range of 80 to 120. For this range of assembly department, we can expect the profit to change by 50 cents, okay, for every 1 hour increments in the assembly department or changes in the assembly department. Okay, so combining all of this information, it's very, very powerful. For example, it already tells you, if I was to make somebody work overtime for 1 more hour, is it worth it? Because based off of this shadow prices, you can answer those questions if it's worth making somebody more in the electronics department versus assembly department, or if at all you should allow them. Because if your overtime cost is more than the shadow price, then probably it's not worth it. Now, similarly, all of these shadow prices are only valid within this range. If you were to go out of this range, the solution of 30 and 40 will change, which means beyond the ranges of allowable increase and allowable decrease, the optimal solution, the best possible solution of the number of xpod and blueberries will change, and so might the shadow price, which means below 200 units of electronics department, the shadow price might be anything different than $1.50. Anything below the constraint assembly of 80 hours a week, the contribution of 50 cents to the objective function might be other than 50 cents. Okay. Now, it also says if we were to change anything in terms of, let's say, $7 and $5 worth of cost, the price, then too much. Okay. Now, for the decision variable x1, which is d5, so just to make sure we are talking the same, the maximum increase you can go for the $7 is 3, which is from here. Okay, 3. The allowable decrease is 0.33, which is 30 cents. Okay, so you can go 33 cents below $7 and $3 above $7 and still be making 30 of xpods and 40 of blueberries. However, or instead of changing the xpod price, the most you can go above is 0.25 for the blueberries, or you can go below by $1.50. Okay, so the range for blueberries is 3.5, which is $5 minus $1.50. Yeah, so allowable decrease 5 minus 1.5, that's 3.5, to $5 plus 25 cents, 5.25. Now, one thing you have to be very careful is that sensitivity reports considers only one change at a time. So all of these conclusions are valid when you're considering only one change. So all of this information is valid when you're making 1 unit change in the right hand side variable, which is this. Okay, and all of this information is true when you're making only the change in this right hand side variable constraint for the electronics. All of this information is true when you are making the change in one variable, which is the coefficient for the xpods, and all of this information is valid when you're considering a change in this $5 for the price for blueberries. We at no given point in time can we say that, okay, we decrease this value by 50 cents and we increase this value by 50 cents. In that case, our corner points will change and the overall feasible region on the graph will change, and we cannot combine all of those information together. We have to keep that in mind. Okay. So now, by this time, we have considered everything that is possible in terms of solving the problems using linear programming. We have used how to solve the problem algebraically. We have which is by solving through the equation. We have seen how to draw the graph and solve the problem graphically. We have also seen how to solve the problem graphically in Excel, such that you draw the points or the values that you want to plot, and you pretend, or you make the Excel pretend that these are lines and not the graphs. Okay, and we also use the Excel solver to help us find these values instead of us doing the calculations over and over again. And after solving this problem using the Excel solver, we looked at the sensitivity report, wherein we also understood how to interpret this sensitivity report for our problem. Now, the only difference moving forward can be that instead of maximizing this profit, if this was to be a cost given, then we will try to minimize it instead of maximizing. So for the next couple of videos or examples, we will not go through in that detail. We will just start using the same pattern of about this much area that is shown on the graph, and we will change it to our benefit and take the advantage of this pattern. So far, the only things to remember is sum product to calculate the profit, and using the similar formula when we calculate the left hand side value for any of our constraint, such that it is at relatively same position. The only thing that changes is the cells to the left, but the reference to the decision variables stays the same.